This video is on electron configuration. So we are going to talk a little bit more about the quantum model of the atom. So when you have looked at the atom before, probably all you know about the atom is that we have our nucleus in the center with those protons and neutrons, and then we have those electrons outside of the nucleus. Now, in middle school and maybe other previous science classes, you talked about those electrons existing in certain energy levels, and that's about it. Well, in chemistry, we go a little bit further into that, and we're going to talk about how we picture those electrons, because our idea has changed a whole lot. So originally, we thought of the electrons as being like trains on a track. And we'll mention this when we talk about the Bohr model of the atom, presented by Niels Bohr early on in the early 1900s. And he thought it was we kind of refer to it as the planetary model, where you have the electrons that are circling the nucleus like trains on a track, or like the planets orbit the sun. And it must have seemed pretty perfect that we would find something in the small world the same as what we found in the big world. But it wasn't to be so simple. First off, well, this is a two-dimensional picture of something that exists in 3 dimensions. Atoms are 3-dimensional. And so this isn't a ring around the atom, but more of a sphere around the atom. And it gets a little more complicated than that, because those electrons don't act like things in the big world do. That they're a little weird. They kind of exist as a particle and a wave, and that makes them harder to describe, and we totally underestimated them. But we do find that electrons do exist certain distances from the nucleus, and we do still refer to those as energy levels. So in the quantum mechanical model of the atom, electrons can take on only certain energy values. So we will find electrons this distance away, and this distance away, and this distance away from the nucleus. And we won't find electrons in between these energy levels. That's because the energy is only in certain packets, and you can't have half a packet of this certain energy. So we do have these energy levels. They're also referred to as energy shells. Now, I don't use that term a lot, but it is a good way to think about it, because, again, they're not like rings around the nucleus. It's more like a shell, like an eggshell around the center of an egg, so and more in a sphere shape. That's at least a very simple way to think about that, but it is referred to as an energy shell. As well as an energy level. Now, electrons with lower energy exist closer to the nucleus, and we number these energy levels 1 through whatever, and we always number them from the nucleus out. So we'll use the symbol N to mean energy level. So N equals 1 is that first energy level closest to the nucleus. N equals 2 is that next energy level. N equals 3 would be the next energy level, and then so on and so forth as we get further away from the nucleus. So those with higher energy are going to exist further away from the nucleus, and those with lower energy will exist closer to the nucleus. Now, beyond energy levels, we can also, as we were looking at Bohr's model and tearing it apart so that the electrons aren't like trains on a track or like planets orbiting the sun, the reason that failed, although it works perfect for hydrogen, it doesn't work for any other element, but perfect for hydrogen, we found it didn't pass the power of prediction. If we were looking at an atom, let's say with 3 energy levels, and we had an electron here and detected it, we would expect that maybe it would be here a little bit later on, but it didn't, using Bohr's model of the atom. So we had to develop this quantum model to really describe these weird little electrons, because they're not like trains on a track. And so what we ended up with is we use quantum numbers to do that. And our first quantum number is the energy level. Our second one is a sublevel. These are mathematically drawn areas of probability. So these shapes do not exist within an atom. They are mathematically drawn areas of probability that describe the most probable location for an electron. So we can only describe the most probable location. We can't tell exactly where it is. And so the way that we describe the most probable location for these electrons is we have different shaped areas of probability. And we call these differently shaped areas of probability orbitals. We gave them pretty simple names, S, P, D, and F. S orbital is this nice sphere shape, again, a three-dimensional circle. And so the electrons would be somewhere on the surface of this three-dimensional sphere. A P sublevel, again, a mathematically drawn area of probability. You're not going to find this dumbbell shape within an actual atom. It's just where we're going to detect electrons of a certain energy. Would be somewhere in this dumbbell shape. In d orbitals with even higher energy are going to be in what kind of looks like a four-leaf clover, all except for this kind of weird one right here. But that's the deal with probability. Sometimes it does develop some very strange shapes. All right, so this picks up on page 17 of your notes packet, and we're going to talk about how we describe these electrons. And so first, I need to give you some information, and the easiest way or most organized way is through a table. So we're going to look at these energy levels, and we're going to talk about the maximum number of electrons in each energy level. I expect that you know this or have already heard this from some of your other classes, previous science classes that you've had. And then we're going to layer in this idea of these sublevels, or what shape of the orbital or mathematically drawn area of probability we have for each of these energy levels. All right, so the first energy level, the one closest to the nucleus, can hold a maximum of 2 electrons. And it only has an S sublevel. So its mathematically drawn area of probability is a sphere shape. And we can find those electrons somewhere on the shell of this sphere. Energy level 2, so the second one out from the nucleus, can hold a maximum of 8 electrons. The second energy level has its own S sublevel, so another sphere much larger than the first one. And it also has a P sublevel, which is that dumbbell shape. So it will have both of those as mathematically drawn areas of probability where an electron is most likely to occur or to reside. Energy level 3, so the third one out from the nucleus, can hold a maximum of 18 electrons. It has its own S sublevel, its own P sublevel, and a D sublevel as well. So much more areas of probability there. And if we have the fourth energy level, it can hold a maximum of 32, and it has all 4 sublevels, S, P, D, and F. The higher energy levels just kind of repeat energy level 4.